So our Friedel crafts, you know what? I think I spelled Friedel differently yesterday on the board. I feel like that is not my fault. That's just the fault of the name. We're doing an alkylation. Can someone just quickly share how we know this is an alkylation reaction? Adds an alkyl group. And an alkyl group is different from an acyl group how? An acyl group has something an alkyl group doesn't. Sorry? No carbonyl. Because it could be a ketone that we make. All right. I also want to point out that we are introducing isobutyl chloride. But we don't end up with an isobutyl alkyl attachment. Strange? Do you already know what's going to happen? What happens, Alec? We're going to see a hydride shift. Because we know the Friedel-Crafts intermediates have carbocations. And a true carbocation intermediate, it will rearrange to whatever is most stable. So step number 1, activation of the electrophile. Don't be surprised when the activation of the electrophile here looks exactly like the activation of the electrophile in our halogenation mechanisms. So I start with phenyl bromide doing nothing, but isobutyl chloride. Remember, chlorine's got 3 of those lone pairs. Isopropyl chloride attacks with one of its lone pairs, forms a complex with aluminum. This looks so similar to what chlorine did with aluminum chloride yesterday. Looks very similar to what bromine did with iron 3 bromide yesterday. But the difference in the activation of the electrophile here is that we have a second step. Now I guess maybe this didn't need to be called 1A, because I often will give you those like 1A, 1B, if they are sometimes plausible or possible but not always happening. This actually always happens. Good morning. We will always see a carbocation form. Our electrophile is not done yet. Because if our electrophile was done, then our ring should just be able to attack that primary carbon, and we should see an isobutyl group attached to our molecule. Instead, we see the chlorine take its electrons from carbon, leaves us with a primary carbocation. Not ideal, especially when we are adjacent to a tertiary carbon. So we should predict a carbocation rearrangement, and of course, we expected a carbocation rearrangement from the beginning because we knew that we didn't end up with an isobutyl group. Adjacent to my primary carbocation is that tertiary carbon. Hydride shift. Now I have a tert-butyl carbocation. Do you guys see the notes in the mechanism where I said alkylation only for the carbocation rearrangement? The acylation mechanism has a resonance stabilized intermediate. And resonance stabilization is always more impactful. So we will never see acylation rearrange, but alkylation can rearrange. Other things I want to point out. My ring played no role. Good morning. Since the ring played no role, I really didn't even want to waste the time drawing the ring. So I just abbreviated it, and luckily, because it's a mono-substituted benzene, I can just abbreviate it as PHBr. I also abbreviated my aluminum complex, except I'm realizing I didn't draw the aluminum complex at the end of step 1A. I personally am an advocate for showing every single reagent at every single step, regardless of whether it actually plays a role in that step or not. Although I do forget my byproducts a lot, so point those out to me if I ever forget. Those are something you can always go back in and kind of fill in as you move through a mechanism. But I like to show everything at every step so I know I haven't forgotten something along the line. Once again, we have our nucleophilic attack, our addition step, our break aromaticity step. I can't just show my abbreviated structure anymore. I need to show the ring and I need to show the pi bonds, because during the nucleophilic attack in EAS, the ring is the nucleophile. Does it matter which pi bond I have my arrow start from? Justice says it matters. Does anybody think it doesn't matter where my pi bond, where my arrow starts from? Which of the 3 pi bonds? I think it doesn't matter. I could start my arrow from any pi bond. Why do you think that? I'd love to hear your thought. What were you on track thinking?
I was thinking that we didn't already have a product, and bromine is ortho-para-correcting, so we have a product.
Great. So if we didn't know which structural isomer we were making, we know that bromine can direct ortho or para, which means this carbon could attack using these pi electrons. This carbon could attack using these pi electrons, or this carbon could attack using these pi electrons. Because any of those 3 positions are plausible, any of the 3 pi bonds are plausible. That's not true if we have a meta-director, because the meta-director would need to use electrons associated with the meta-carbons, and so it'd have to be limited. But we have a specific structural isomer that we're going for. Therefore, we need the pi bonds that are associated with that carbon to get that structural isomer. Fair? So we know that this pi bond is going to attack. Yesterday, I started doing that when we had the oxygen donating group, the ester connected by the oxygen. And I said, we know what structure we're going for, let's start from there. But I want to start from the other side this time. Bromine is an ortho-para director. Why is it an ortho-para director? Why does the lowest energy activation barrier follow ortho-para positioning relative to the bromine? It's because bromine, despite pulling electrons out by induction, by electronegativity, it can also push electrons in from its lone pairs. Remember, the halogens are not an electron donating group, but they're also not an electron withdrawing group. Do you remember the difference in energy where halogens fell in terms of activator, deactivator? Slight deactivator. So they tend to pull electron density out more than they share, But when they share, they can stabilize those ortho-para positions. So I'm actually going to start today by showing bromine's role in this mechanism is to push electrons into the ring despite pulling electron density out by induction. And that will allow us to attack from our para-substituted carbon. By the way, you don't have to draw your arrow this way, but I've been trying to find ways that you can draw arrows through the carbon that's actually going to use the electrons, because we know that these electrons are held by both carbons, but only the para one is going to use it. You can try and draw it through that carbon. Once again, I like to draw my my hydrogen on that tertiary carbon, excuse me, on that sp3 carbon. Little positively charged bromine to start the day. That's the only resonance form that I'm going to draw, because that is the major resonance form. How many other resonance forms are there in the structure? Do you remember when we showed the mechanism with just benzene acting as a nucleophile? How many resonance forms in the sigma complex intermediate when it was just benzene as the nucleophile? No substituents. That'd be your first mechanism from yesterday. 3 resonance forms. Where are those other 3 resonance forms? They're here, they're just minor. Because I could put a positive charge here, misses octets. I could put a positive charge here, misses octets. And I could put a positive charge here, but again, no full octets because positive on carbon lacks an octet. And what does this form give us? Full octets. Just like when oxygen shared electrons, just like when nitrogen shares electrons, bromine gives a full octet by taking that positive charge. If you want to show all 3 of them, am I going to take off points? No, that's crazy. You can put in the work and do that, that's fine. In fact, I used to require that you show all resonance forms regardless and circle the major one. I don't require that you show all resonance forms, but you're welcome to. This, to me, I think this conveys more than what showing all resonance forms can do. This tells you why bromine is orthopara directing. Okay, major resonance forms, already done, so I'm just going to check that off. And we're on to our last step, which is different ways to consider it. Deprotonate the ring. You can think of it as elimination. You can think of it as reforming aromaticity. And it should come as no surprise that this step looks exactly like our chlorination mechanism. Where one of those chlorines takes electrons back from aluminum. And now my resonance is going to push electrons. It's not resonance, sorry. Because of the resonance form I have, I'll need to push electrons all the way back to the bromine. If I had shown a resonance form where the positive charge was right next to the group, I would have had fewer arrows. Kind of. I would have also had to draw more arrows to get to that resonance form. Do you guys see what I've forgotten on the board? I've missed something in my structure. Yep, I forgot my positive charge on bromine. Once again, you are welcome to take the lazy route if you want to, and you can just draw that circle at the end of the mechanism. Because we're done. We're done with the mechanism. Okay. Now I want you guys to take a stab at acylation. I gave you some notes yesterday about acylation. I told you what the intermediate looks like, the electrophile intermediate. I told you that the electrophile is a resonance stabilized electrophile, and that one of those resonance forms is more major than the other resonance form. This is why there's no rearrangement in the acylation mechanism, because the electrophile that forms, that positive isn't even held by carbon, it's shared by oxygen as well. So there will be no rearrangement. You could show me either of those resonance forms in the mechanism, I would accept it, but there's one resonance form that makes more sense. Which of the two resonance forms on the top right up there makes more sense? Is it makes more sense, maybe isn't the right answer. Is a better contributor to the structure. The left structure. Why? Fair enough. But I can't really attack that oxygen anyways. It has a full octet. But I could still attack the carbon in the resonance form on the right. What I can do to one resonance form, I can do to another, because two resonance forms don't exist. So any limitation presented by one is just as present in the other. I would say the one on the right is a better contributor. But this is why I'll accept you showing either one of those resonance forms in the mechanism, because as Alex said, the ring is going to attack the carbon. So putting the positive charge on the carbon is going to draw your mind to attacking the carbon. But the structure on the right maximizes octets. All right. Take a stab at this mechanism for acylation, and I'll come around and answer questions and see whether you guys are on the right track. What did you? Do you want a physical one?
I think I left my pencil in the corner.
Oh no. Good start. Got that lone pair shown. Good start. On the right track, looking good. It's coming naturally to you guys. 8 a.m.'s got nothing on your brains. Just mine. Mm-hmm. Isn't that fun looking? Great job of getting there too. Those are the arrows we need. Good work, Alec. Could see those gears turning. You were mapping your carbons. You were keeping track of which one actually lost the bond, which one actually takes on the positive charge. Now, which of those resonance forms have you just drawn? Yeah. And you could think about what extra arrows could you add so that you form the one on the right away. But what you have is enough. You could move on to the next step with that. Yeah, okay, you know what? Earlier I said I like to see everything at every step, even if it doesn't play a role. But now you're drawing that like dye substituted ring every single time. But I can't have you draw the dye substituted ring as an abbreviated pH because it doesn't give me the structure. So you don't have to, I like to show, I should say. I like to show everything at every step. But you don't have to in a mechanism. If something doesn't play a role until a specific step, you could leave it out. But I think it'd be better to leave it out than try to draw it like this. Because is that ortho? Is it meta? It doesn't look para, but how can I know? I really can't. Good. Now, which of those resonance forms have you shown? Right. So you could move on from there. You could think about what other arrow could you add to have automatically formed the one on the right. Right? Because any resonance form can be used at any point. Good.
Sorry. Just draw this arrow down at this point.
Mm-hmm.
Got it.
Got one too many arrows. Okay. Think about how many bonds between carbon and oxygen you want to have. Do you need to make a bond to make that happen, or do you need to break a bond? Because what you're doing here is both making and breaking one of the bonds. Mm-hmm. Now you're just thinking about how to get to that carbocation intermediate, right? Yeah. Or really the oxonium intermediate. It's going to look, well, it's going to look nearly identical to this, but you don't have your arrows here. Right? Yeah. That's an important arrow. Yeah. This is all we've done. You haven't missed anything.
Which one are we doing?
So the one on the left is the alkylation. We went through that one together, and I'm having them do the acylation. So you might want to start by just following the alkylation. It might not give you, you might not have the chance to guess at the acylation on your own, but they're very similar. They're like nearly the same mechanism, but small differences. This is perfect. This is great. Do you see how you could add this arrow here and automatically get to that resonance form? Yeah. This works perfect. Nothing wrong with even getting to that. But if you want to show this right away, there's one less step to do. Then we're forming a bond to a carbon that has an octet. Yes, great. Do you see what's funky about it there? The 5 bonds. I mean, it looks kind of cool. Before you get too far, this is great. That's exactly what it forms. That's the resonance form on the left. When you attack it, that carbon is hungry for electrons. It doesn't have an octet. So when it gets attacked, it has no reason to give up more electrons. If it did, if this bond broke, would you agree that this oxygen is going to become negative, and this carbon, which currently has only 6, takes 2 more but gives up 2, is still going to end up with 6 and be negative?
Yeah.
So this arrow shouldn't be there. And that CO double bond is maintained in the final product. Right? Good. Good work, Evan.
I don't know
Mm-hmm.
what to do from here.
Yes, you have not explicitly drawn in your assumed hydrogen, and that can be a point of, like a sticking point. Do you know what I mean?
Yeah.
What did you change?
Oh, I see.
Okay, good.
It's just all one C.
So that if you draw it out, it draws your mind to it, and then you go, oh, I got to do something with that.
Yeah.
Great. But you haven't shown me the major resonance form. And remember, that's one of the big parts of these mechanisms. So I want to see the major resonance forms. This is minor because lacks octets.
So you want like the oxygen to donate?
Well, actually, the NO2 group is not connected by the O. It's connected by the N. But if you draw out the NO2 group, do you know what you get? Perfect. And in an aromatic ring, that can pull electrons out, but it can never push electrons in. So that NO2 group involved in your major resonance form? Definitely not. In fact, the NO2 group is a meta-director. If it were the primary, if it were the strongest activator, it would be a meta-director to avoid ever being close to the positive.
That's not in.
Never going to be involved in it. Nope.
Okay.
Yep. You got it. Yours is done. Can I answer other questions? You guys are just chugging away.
Would you, I'm just, like, would you use this one though? Or if you wanted to use this one, would you still just attack right there and with that?
Mm-hmm. Yep. Yeah, so using the more stable resonance form means showing more arrows.
Right.
It does.
Okay.
Because you're going to have to form that triple bond and then break that triple bond.
Yeah.
But you guys see why this is a linear structure, right? That's an sp carbon. It's got a triple bond like an alkyne. But without drawing it in that resonance form, a lot of you are showing it like this. That's still an sp carbon. It has no other electron region repelling the other two, so the two regions repel each other 180. So in my opinion, this is, one, it's a major resonance form. It stabilizes the octets. It explains why we have no rearrangements. It explains our geometry. So it does require more arrows. I don't know where I was going with the rest of that sentence, but yeah, I would, but I'm okay with taking either.
Or what if I just like show it, but then still use
Yeah.
this one because it like makes more sense to my brain?
Either one. I would say if you want to use the one on the left, then you don't even have to go through the work of showing me the one on the right.
But I
That's fair.
embarrassing.
That's why I'm here.
I'm trying to figure out where I messed up.
When a bond breaks, it always breaks toward the more electronegative.
So then technically
But where you messed up was
this part.
creating a carbon. Carbon to chlorine, acid halide.
Mm-hmm.
Carbon to chlorine, carbon to carbon, ketone.
Oh, okay.
Good morning.
Does that make any sense?
Yes, although I would say that this arrow doesn't go to that carbon.
Oh, it goes.
It goes to the next bond.
Because we're making it.
You're making that pi bond there.
Okay.
And that maybe it will explain what you're
Okay.
stuck on in the ring there. Perfect. Yep. And then the only thing you have left is show your carbonyl. Right now you've got a alkene. Right. Good work. I like this idea that you're taking, Esmeralda, to, you know there's going to be a major resonance form, and you're just kind of pausing, know how to do the elimination, which is good, and you're coming back to fill those in, right? Okay, good. Evan, is that a raised hand? Ah, you know what, actually, well, sorry, are you done drawing? Okay, a couple of things. When your nitrogen formed a pi bond, it looks like it formed a pi bond. Yeah. Do you see how it looks like it formed a pi bond into the ring rather than with its carbon? There you go. Wow, that's a nice program. Do you guys that draw on your iPads, do you ever feel limited when you, well, maybe you don't know yet, when you have to solve it on paper? Do you feel like the skills don't transfer as well between paper and tablet, or do they transfer fine? Fine. Evan just showed me how he can just move his arrow around just by clicking on the arrow. He doesn't have to erase and redraw it. You're not going to do that on the midterm, unfortunately. Okay, now I want you to think about how... Yes, you took the words right out of my mouth. Brenna, do you want to grab a picture of the board first? You did, okay. You bet. Okay, who else can I look at? Whose have I checked off? Who's done? Is yours done, Jaylee? Ah, well, this nitrogen, 2, 4, 6, 8, 10. That nitrogen doesn't have a lone pair. Remember, it looks like that guy down there in orange? It has a positive charge because all 8 of its electrons are used in bonding. So the nitro group can pull electrons out, but the nitro group will never push electrons in. But an amine has a lone pair on the nitrogen that can be pushed in to make a double bond. Justice, yours is done, right? Have you started on your synthesis? Oh, that's what you're done with your synthesis. Okay. Well, Justice is going to go around and help you guys answer questions.
I don't know what to do from here.
You're perfect. That's your major resonance form.
It is?
Mm-hmm.
Oh my gosh, I've been sitting here looking at it. forever.
Now you need to do step 3.
Okay.
Yep. Yes. Okay, so you figured it out. Ah, and then you rearranged.
No, so what did we range?
only in alkylation.
This is alkylation.
Yeah, where we add an alkyl group. This is
Oh,
acylation.
so it wouldn't rearrange.
And the
So
question
like
and the
this.
question is, why wouldn't it rearrange? Well, first of all, notice how if it did rearrange, Mimi,
It wouldn't add on to the.
it wouldn't add in the right spot. Yeah, the ring would attack from here, and we'd get a structure like this, right? I mean, that's a weird looking way to show it, but I didn't actually make an aryl carbonyl. It's not connected to the aromatic ring. The other reason why it doesn't go here, tertiary carbocation, okay, how about resonance stabilized carbocation, one with maximum octets? This is far and away more stable. To do that rearrangement, you'd have to go from this resonance stabilized intermediate to this tertiary intermediate. It would be more stable to go the other way, but I don't think I've ever seen that. Do you guys like this struggle? The challenge? I just, I think in the past I've handheld a little too long on mechanisms and just let students copy down, and it kills some of the creativity that needs to be there with mechanisms. And so you rarely get a chance to struggle in front of me so I can give you immediate feedback. When you get onto the homework, and if you submit your homework Monday morning and then take your unit test, I can never give you feedback before you actually have to do it on the test. Yeah.
Can you explain to me how, because this then looks like bent again, right? It's not like straight
Yeah.
anymore?
It goes from 2 electron regions back to 3.
Okay, so that's why.
Yeah.
Okay, that was all. Because I'm like, I don't understand why it's bent again, but that makes sense.
You got it.
So are you basically saying that it's just gonna go like that,
Mm-hmm.
and then the oxygen won't carry the.
And you could even do that arrow here
Oh, okay.
and just form that resonance form right away. Or you can just go with this. You can have the ring attack that because both resonance forms fail to represent the structure. Great. How many carbons connected to your carbonyl?
Right here?
Yeah, because I see a line going off to the right.
Would there not be one there?
Well, I don't know. Let's look up at your last structure.
That's what I've been stuck on.
Oh, there was a chlorine there. But the chlorine left.
So there wouldn't be one right
So there wouldn't be.
Okay.
So now it's just a hole on that carbon, which means it would look like this. So I'd given you that feedback earlier. If you had an arrow coming down from O, but then you also had the CO double bond leaving. If you had the double bond from O, or sorry, if you had the lone pair coming down from O, you make the triple bond while the chlorine is getting kicked off, giving you that resonance form on the right.
Okay. And then I could just interchange between the two?
If you want to, or with the arrow that you have here, just the chlorine leaving,
Mm-hmm.
it would give you the structure on the left.
Okay.
If you want the structure on the right, you just add one more arrow coming down from the O.
Okay.
Neither are wrong, both are good. Did you find that resonance form? You sure did.
Okay, the whole time I had it as NO2.
Oh, you had it both as NO2s.
Yeah, and I didn't realize until I think you drew something up there. I was like, oh, it's NH2.
Good. Okay, great work. And then you, yeah, you made it happen. Great job. Mm-hmm. Yeah, so this is something Mimi brought up to me. She had a professor that would never, ever, ever allow drawing arrows from lone pairs, or sorry, from charges.
Oh, okay.
Only ever lone pairs, even if that means just drawing in the assumed lone pair that the negative charge implies. And this is the primary example of why we shouldn't draw from the negative charge on aluminum, because aluminum is not using the electrons. We should draw from the aluminum-chlorine bond because chlorine is using the electrons. And by starting from the negative charge, we don't show how the bond is breaking. Since it's a bond breaking, we have to start from the bond, despite there being a negative charge. Good. Okay, yours look good. Yeah, much, much better. And you see how the nitrogen now is serving as the para director.
Yeah.
Good. You're coming for the wrong. Yeah, let's look at your resonance form. This resonance form is perfect, but this resonance form is not this resonance form. And I think maybe this one came from the last structure where you were showing NO2 involved. Is that true?
Yeah.
So take this and move it down here, because this is the right form and this doesn't exist. I want you to notice the difference is an sp3 hybridized carbon. An sp3 hybridized carbon. And the sp3 hybridized carbon has that hydrogen on it. That's the hydrogen that needs to be pulled off. In your step, you're deprotonating hydrogen that shouldn't be pulled off. So I would recommend drawing in that assumed hydrogen. We're substituting, like here, we're substituting this H for tert-butyl. None of the other H's leave, but this H will need to leave. So wherever your new group is coming on, that hydrogen needs to be deprotonated. I guess the other thing you could do implicitly in your mechanisms to try and make it all make sense more is always draw that H the whole way through. The H that's going to be pulled off, draw it at every step so that you keep thinking. All right, I'm gonna show this mechanism now if you guys are ready. I think I saw some really good productive struggle there. Absolutely. If you don't believe in productive struggle, then I hope I can teach you to believe in it. I would say that the difference between busy work and productive struggle is that you walk away stronger from productive struggle. You don't always walk away stronger from busy work. I wasn't just keeping you busy. I'm making sure that you can do your homework tonight and that you can do the unit test this weekend. That's what I saw, is that you guys could handle anything that comes your way now. Okay, I'm going to show this all as one sequential mechanism. I hear you guys, although you're not saying it, I hear you about not wanting to draw out that ring at every step, so I will follow suit. I'm going to show just the activation of my electrophile. Either one of those is fine. If you form the resonance form on the left, it's just the chlorine leaving, just like what we saw with the alkylation. That would leave me with two groups off of this carbon and a positive charge. But oxygen sharing its lone pair is going to make this leaving group leave even better. And that gives us that triple bonded resonance form. And at this point, my aromatic ring comes into play. A lot of you recognized at some point, either early on or after trial and error, that the amine is the activating orthopara director, and that the NO2 plays no role in this mechanism at all, because it is an electron withdrawing group. So for a reaction where the ring needs electrons, the NO2 can't help. How many lone pairs on that nitrogen in nitro? How many lone pairs? 0 lone pairs. How can it donate electrons in? It cannot. It can pull electrons out, but it cannot donate electrons in. Now, once again, I'm trying to show that my pi bond is attacking through the pair position, just to give you guys a way to see that you can try and visualize it, but it doesn't really matter. Because I added the extra arrow to make the CO triple bond, I need to add an extra arrow to break the CO triple bond. If I had done this with the positive charge on carbon, no other arrows necessary. If I had done this with just a double bond on carbon to O, and I showed it a bond breaking to O, I'd create an O minus, and I still wouldn't get an octet at carbon. So this arrow is only necessary with this resonance form. How many other resonance forms exist for this structure that I'm not showing? Three. Thank you. You're getting good at it. Stole that from me. I was gonna. Sometimes I forget, sometimes I do it intentionally. There's 3 other resonance forms, all minor because carbons lack their octets. So 1, this is the reason that the ring attacks from this position. It's because of the nitrogen. And it's because of this most stable resonance form that we have our activating group in the first place. All right, I'm actually going to draw my hydrogen down here so that I can show my deprotonation a little bit easier. And then lastly, I do say almost all the time you can draw an arrow from a negative charge unless you need to show a bond breaking as well. And in this case, the negative charge is held by aluminum. The bond breaking is from chlorine taking the electrons back. So we do need to show the electron arrows starting from the chlorine bond, breaking back to all the way through the ring back to the donating group. Oh, and the last thing I wanted to add here was no carbocation rearrangement because we have that resonance stabilized carbocation. It's more of an oxonium ion. Okay. The rest of the time is yours to do the synthesis on the back. What I want to remind you of is that you need to pay attention to directing effects. You need to be able to add something that has the directing effect that gives you the structural isomer that you want at the end. There are reactions from EAS, NAS, benzylic reactions like benzylic oxidation, benzylic reduction, and there very well could be other stuff. Oh, down on, I did this because I love to see you guys like get exposed to a lot of different structural drawings. This last structure on the bottom right of the structures given you might want to draw out what that bond line looks like if interpreting condensed structure is not easy for you. That's not just a 3-carbon chain. There's more going on in that system than just that. I worry I messed up on it. Sorry. So I will figure out if I messed up. I'll get back to you guys. But for now, work together, collaborate, use your resources, use those reaction diagrams that I've given you. The rest of the time is yours. Why did I do that? Why did I do that? CH2, CH, CH2.
That will be a single bond, not will be double.
It should be a double bond to the end.
Yep.
Okay, okay. Good. Yeah, the problem with that last one is what I told you guys yesterday about. So what did I screw up here? Yeah, I did screw up. Can we make this change? I think I have to make this change to that bottom right structure. The product will have a bromine instead. And then the CH2CH2. And I can't tell you why until you solve it. By the way, this is the most time I've ever given to a class to do synthesis practice on this topic. I don't know what we did, but we moved through this unit faster than I've ever moved through this unit before.
Just really smart.
Yeah, just a brilliant class.
I don't know what to do with this guy right here. The anhydride.
Here?
Yeah.
Well, it's on our packet.
Oh. It just does that?
Yeah, it does the same thing as that mechanism we just drew. So I just want you guys to have diversity of examples. I want you to see things you're going to see in other places. Oh, you know what? There's something I think I forgot to share that will be on active.
Yeah.
Yeah, if you'd rather work on the written work, homework, and turn that in before you leave class, you're welcome to do that instead of this packet. You have that choice. On active, you have a problem that has an anhydride, which we know does acylation, similar to what the acid halide does. What a cyclic anhydride does, though, is that it gives you both a new acyl group and it gives you a carboxylic acid, which is fun, but it then gives you a reagent that I have not given you for a carboxylic acid before. I've given you this reagent for alcohols, but we know that alcohols are not carboxylic acids. So the fact that the OH of the alcohol and the OH of the carboxylic acid do the same thing here is coincidental. Converts carboxylic acids into acid halides. You guys will see that problem on active, and it's one that I will not probably put a problem on like that on the midterm. But we will do that reagent and that conversion in lab later in the semester and in lecture later in the semester. So that's going to help you on active. And then again, this is on the bottom right of your worksheet. No, I don't. I don't ever want to hold paper, to be honest. To hang on to it is, what am I going to do? Throw it away? You can throw it away. But if it's not on canvas, then it gets really easy for me to lose it. Good work. You guys all have the mechanism down? Anybody still working on the mechanism? Okay, I'm going to clear that out. I am thinking about how these last three, where you're drawing products, if you have something that could give structural isomerism, you could either show both structural isomers or lean into one and just follow that one through.
What kind of effect does this have on like the directing?
Well, they are two different groups, so they have two different directing effects.
So that would be like electronic drawing.
Mm-hmm.
So meta, but that one would be ortho para activating. So I go with that one.
Good.
Okay.
Look for your strongest activator. Just like you had to do above, right?
Mm-hmm.
Exactly. Great job with figuring out that. That's great.
This is not what you were looking for, but does this work?
It doesn't. It doesn't work. One, where did the carbon go? If anything, it would actually turn it into benzyl alcohol.
I thought this reduces an aldehyde to a primary alcohol.
That's right. This is not a primary alcohol. That's an aryl alcohol. Do you see how you lost your carbon?
Yeah.
No, it's a good thought. How do we get oxygens onto the ring? Well, any way to see oxygen getting onto the ring by EAS?
Carbon.
Yeah, just carbon. How about a way to get oxygen onto the ring with our last reaction? That's an oxygen group. So EAS does not connect oxygen to the ring, but NAS does. What do you need to be able to do NAS? You need a nucleophile. And I mean a strong nucleophile, but not necessarily a strong base. And benzene? Can benzene go through NAS? Why not?
What's it called? Something halide.
There's no leaving group. So to get oxygen onto the ring, you need a leaving group. And if you don't have a leaving group to start with, you're going to have to add a leaving group. I don't know what I messed up with on that last problem. I don't know what was going through my head.
Could I ask a question?
Tell me.
So, these guys are technically ortho-para directors,
Yep.
but in this case, where would it matter where it's added?
Well, actually, there is one. First of all, the product I want you to draw is shown.
Oh.
So you don't have to guess.
Never mind.
But
I didn't even pay attention to that.
two of those positions are the same. Ortho to one OH, para to the other.
Mm-hmm.
This position in the middle is ortho to both. But either way,
You're saying it's ortho to both if you put it here?
no. If you put it here. Do you see that down there?
Oh, down there.
Yeah.
Okay.
That's going to have more steric strain. But it's not like being ortho to both is better than being ortho or para to both. And you don't have to guess which structure to draw. Yep,
That makes sense. Thank you.
you bet. How you doing?
I kind of skipped this one.
Oh, you haven't got the notes yet either?
No, but on this one,
Mm-hmm.
I'm stuck on the resonance form.
That's perfect. If you draw the resonance form that comes from that, You will be drawing the most major resonance form.
Oh. Okay.
You just need to show it.
Like, I just need to show the intermediate.
Mm-hmm.
Is that 6?
Yeah, it is. It's 6 enough.
And then, like, no, wait.
Because you're showing a bond making.
Mm-hmm.
You're showing a bond forming. So show me the bond that forms. Mm-hmm. And then I always like to highlight that hydrogen at that carbon
Oh, this one.
because it's going to be important. All right, now your structure is not quite done.
And then we get the
Mm-hmm.
something, and then it pulls this.
But your structure isn't quite done. You're missing something in your structure. Well, I agree. There should be a positive, but that carbon just accepted electrons.
Yeah.
Which carbon has lost electrons?
Oh, this one.
Yeah, which is why it's your most major resonance form, because it's the most substituted position.
Okay, and then this takes the hydrogen, goes in, and goes in.
Yep, you got it. On your synthesis on the worksheet, you've added a meta director and then tried to add a group ortho to it. It won't add ortho.
Oh, so it needs to add a meta group. Wait, sorry. So it needs to add this first, so that this goes in the meta.
Well, the final product is ortho.
Oh, yeah, ortho para.
Yep,
So I need to add a ortho para.
director first.
Is that a withdrawing group?
Nope,
Donating group.
donating group.
Donating group first, and then go.
Good. Then the other thing is this reaction wouldn't actually proceed.
Okay.
With an electron withdrawing group on the ring,
Mm-hmm.
alkylation and acylation are just not feasible. They require too much energy.
Okay.
They won't happen. So this wouldn't happen anyways, but it couldn't give you that structure, no matter what, even if it could happen. Okay. Who else has questions I can answer? Okay.
I don't know how to do this.
SOS.
On the bottom?
This one.
Oh,
Am
up
I
top.
like on the right track or no?
You would need an extra step if you wanted to do it that way, and you'd need reagents that I haven't given you yet.
Okay. But okay. Is
So what are you?
Because this has to be the. Hold on.
Mm-hmm.
Let me get to these. Because that is that, right? It's a withdrawing group.
That's a withdrawing
So
group.
you want to add that last,
Okay.
right? Or no?
I mean, it kind of depends on their relative position to each other and what the two groups are.
Well, that's not meta.
It's not meta, right? So the nitro shouldn't be the director.
Right. So you have to add that last.
But how does carboxylic acid direct?
I don't know.
Well, is it a carboxylic acid donating group or a withdrawing group?
It's a.
How were you able to erase my text?
I just put white on it.
Oh, clever, clever. Sorry, what'd you say?
I want to say it's donating.
Can you show a resonance form? Do you remember at the end of aromaticity last week, we showed how?
Wait, it's withdrawing. Okay, yeah, I'm following now.
How come?
Because that oxygen, the carbonyl oxygen, if you will.
I will.
We'll pull that up.
Yeah, it's pulling electrons away from it.
Okay.
So that would also make it a meta director.
I don't know.
You're going to have to get an orthopara director and then make it not an orthopara director,
Okay.
right? That's the only way. There is an orthopara director somewhere in the synthesis. You just can't see it because it is changed also in the synthesis. Do you guys want to collaborate? I don't mean for you to just be working alone. If you feel confident on your syntheses, you should go ask other people if they would like pointers or help. Who else has questions I can answer?
So if we're adding a group, is this, first of all, is this making any
The reagents work.
But it's because we're adding meta.
Right.
So
And this is an orthopara director.
right.
So I can't add it first.
Oh, okay, so this part it just can't exist. Like this is gonna make a meta or a orthopara product
Right.
rather than a meta product.
Right.
Okay. So there's one that makes how did
What is this group? How do I know what?
like whether because don't they always add ortho or para?
No, we have three different groups. Electron donating groups, which both activate the ring and direct the ring orthopara. The halogen, which actually deactivates the ring, but still directs orthopara. And electron withdrawing groups, which deactivate the ring and direct the ring meta.
Oh,
Are you in the lab this semester?
I am, yeah.
We did nitration last week.
Oh yeah, it was a meta.
It was a meta director
Oh, okay.
because it was an ester. It was an electron withdrawing group.
Okay, that makes sense.
Good.
When you say activate or deactivate the ring, does that just mean it engages in resonance?
Nope.
Okay.
There's always resonance.
Okay.
Looks like maybe you didn't draw it, but I had this energy
The
diagram.
activation Stuff? Okay,
Mhm.
okay. I see.
So when we say deactivate, what we mean is the activation energy becomes much higher.
Oh, okay.
So the ring itself now is not as reactive. The activation barrier has become larger, deactivated.
Okay, that makes sense.
An activator drops the activation barrier. Now the ring is activated to be faster than before.
Okay.
So with that nitration, we had to keep it cold so that it didn't nitrate again. Despite after the first nitration, it had 2 deactivators. And it still was so reactive that we had to keep the temperature below 0 or below 10.
Right.
Could you imagine if we had an activator on the ring?
Right.
We had 2 deactivators and it was still very reactive. It's not that a deactivator kills reactivity.
Okay.
It's just relative to something that is relative to benzene or relative to some other groups. It requires more energy.
Okay.
So
Makes sense.
if we had tried to do that with,
Yeah.
and you might have seen this in the lecture yesterday, if we had tried to do that with toluene, we maybe would have need to keep it at like liquid nitrogen temperatures to keep it from not dinitrating or trinitrating.
Okay.
But it makes sense that TNT is easy to make, trinitrotoluene, because it's got that activator. And we know that the nitro group deactivates, but we know nitration still happens quickly.
Okay, yeah, that makes sense. Because in my mind, I was like, deactivating means like it's not happening at all, but it's like relative.
It's just relative. Just relative. Good.
That makes sense.
So you know how to solve that one then?
I'm gonna think about it.
Okay.
Yeah.
Okay.
Yeah. Give it a thought.
This is good. That's great. That's great as well.
Oh, okay.
There is also a way to swap these 2 steps because orthopara director. And once that group is on, you now have an electron withdrawing group that helps with this step.
Oh, okay, I see.
So these both work, although you forgot your O here. And I see what you're saying there. It would actually be a benzene on both sides, right?
Right.
Yeah. Good.
Okay, one more question. So this is gonna rearrange.
No, it's not, because the most stable carbocation is already the one that will form.
Oh, in the center. Okay.
Yep.
Okay.
But this one a primary carbocation. N means normal,
Normal?
just a linear chain.
Okay,
Yeah, I know, whoever decided that's normal.
Normal. Okay.
You're welcome. How you feeling?
Good.
Good.
This looks pretty correct.
Yes, but I do want to see the major resonance form.
For this?
Yes. And this is a secondary carbocation, but if the electrons moved over one more,
Oh, it would be
a tertiary, which is why the alkyl group is orthopara-directing, because the alkyl group gives a major resonance form, a more substituted carbocation.
Okay.
Okay.
Okay, I have another question.
Oh, and then I just want to check your deprotonation. Yeah,
Wait,
that looks great.
I thought a major. Oh wait, no, I think we discussed this. Since the resonance forms are all the same, which is on a carbon,
Mm-hmm.
you still want us to show that, show all of them.
No, I don't need you to show me all of them. Well, okay.
Like in this case,
In this case, there is still one that is more major.
really.
Yeah, because secondary carbocations are less stable than tertiary.
Oh, I see what
So a more substituted carbocation is more stable, is a major contributor.
Okay, so that's all you would want to see. Is
Yeah,
the true-
yeah.
that
You're
makes
welcome to draw all the other three, or actually in this case, all the other two, but you wouldn't need to.
sense. Okay, that makes sense. Yeah.
Okay, so electron withdrawing groups are, they don't have like lone pairs or anything. They're like the opposite of a nucleophile.
Electron withdrawing groups have a pi bond.
Oh, pi bond.
Yeah, that's the difference. So I've drawn benzoic acid up there, and benzoic acid has a pi bond conjugated to the ring, as opposed to electron donating groups, which have a lone pair donated to the ring,
Donate. Oh,
except for the alkyl group, which does not have a,
right.
yeah.
Okay. Okay, thanks.
You're welcome. Oh, I think you forgot a chlorine on your structure. Right? Here, you've got CH, CH3, 2. Yeah, perfect. Great job. How does bromine direct the ring? We could look at our mechanism that we did just earlier. Yeah.
So should be the reverse order.
Yeah, because this will direct the ring meta as an electron withdrawing group. Good. This is great. This is good. And sorry, I want you to do it. This is perfect, and these two steps can be interchanged because this is an orthopara director. So is this. So if this group added on the carbonyl, then doing NAS has an electron withdrawing group, which would make it easier to happen. It's kind of like a win-lose situation. You have a donating group, which will make this step faster, but if you swap these, you'd have an electron withdrawing group to make this step faster. Do you agree that this is an NAS step, not EAS? And NAS is activated by withdrawing groups. The nucleophile attacks the ring. Where does that negative charge go? It goes into the withdrawing group. So you could swap them. You could swap whether you add the carbonyl or add the nitrogen. That's all. That's all I'm saying. Although this, I'd like to see its charge. And actually, not like to see its charge. We can't assume charge, so we have to see its charge. Good. I wonder why in this, if you're going to do the oxidative cleavage, why add an alkyne?
That was on the paper reactions. Would it work on an alkene?
It would work on any carbon that has a benzylic CH. You could add methyl, you could add ethyl, you could add isopropyl. You can't add tert-butyl because tert-butyl does not have a benzylic CH. But any carbon is all you need. It definitely doesn't need to be an alkene or an alkyne. It just needs to be alkyl. So I do think, though, that you're adding a meta director and then proposing that they're ortho. Or sorry, you're adding a meta director, but then showing them as para. Do you agree that this is a meta director?
Yeah.
So maybe instead of nitration, alkylation, nitration. Yeah.
I don't know how to do that one. Do you want me to put up on the board that it changed?
What?
Yeah.
You don't know how to do it?
No, because, well, okay, so I know that whatever is that thing,
Yeah.
that little thing,
Yeah.
has to be a meta director first.
Right.
But I don't know how to get a meta director to that.
Well, give me an example of a meta director that could have been.
Well, or maybe like some, I don't know.
Could it have been a sulfonyl? And then turned into a carbon chain?
How do you do that? Do you just,
I don't know. Didn't see it. Could it have been a nitro and then turned into a carbon chain? Could it have been a
carbonyl?
carbonyl and then turned into a carbon chain?
Yeah.
Oh, okay. Great. There you go.
How do you get that out?
Just add it in with the carbonyl.
So if we reduce the carbonyl, does it also reduce the alkene, or is it just the carbonyl? Oh, just the carbonyl, huh?
Just carbonyl. Yep. Okay, any last questions before I start putting solutions on the board? Because I want you guys to walk out with answers to these and not have to guess. And I also just don't want to have to upload an answer key. Okay, you ready? Number one, our products have ortho substituents, so we need an ortho para director first. This is a meta director. This is an ortho para director. So I need to add that guy first. Obviously, the easiest way to do that is by alkylation. And just take the alkyl group you see and just add it like that. There is another way to add this. If you added N-propyl chloride, it would just rearrange. You cannot get a primary carbon attached to the ring by alkylation. Then we have nitration directed ortho by our alkyl group. In the second one, I have a meta di-substituted product. This is a meta director, and this is an ortho para director. So this time, I need to do sulfonation first. Remember that our electron withdrawing group, they deactivate, but that doesn't make it impossible to run it. It just means usually you need more energy. In this case, or they also deactivate too much for alkylation and acylation, but in this case, we're doing halogenation. So we just add Br2, FeBr3, and we get our meta substituted product. Now in the last one, I cannot use EAS to add an alcohol. I promise you, I will never trick you into thinking that there's an EAS way to get an alcohol on there. The only way to get an alcohol on is by NAS. Any oxygen group, sorry, not just alcohol, but any oxygen group would need to be O-, some strong nucleophile. And NAS requires, I was asking you about this earlier, Alec, requires a leaving group, right? needs to have a leaving group on it. So maybe that's chlorine, maybe that's bromine. Which one would have been more accurate, chlorine or bromine? Doesn't matter. It's the fact that you have a halogen. That's what we want. Fun, right? Okay. I have seen too many students that will try and show H2O plus or H2O and H3O plus to get an alcohol as if it is an alkene addition reaction. You can do this. It forms two different layers, benzene and aqueous layer, and nothing happens. So please never think that alcohols or oxygens get onto the ring any other way than by SNAR, NAS. Okay, in our next one, 3 steps, 2 intermediates. I know that I've got ortho groups, so I'm going to need an ortho-para director at some point. And the carbonyl is a meta-director, so that's going to have to go on second. The nitrogen, just like the oxygen, has to be produced by NAS. So I need to get a leaving group on here. Let's add a bromine. And now let's consider, I could introduce my NH2 minus group. And I could substitute the bromine, and now I have an ortho-para director. I also have an ortho-para director already. So I could add the carbonyl now, and when I do NAS after, I have an electron withdrawing group that will help NAS proceed faster. So there are 2 correct answers here. One is do NAS and then do acylation. The other correct answer is do acylation. I'm going to show you that there are different reagents that you can use for acylation. And then do NAS. It's not just one synthesis. There's more than one route. And I often say that there may be more than one correct route. Not necessarily. This step is going to happen faster because I have an activating group. But this step is going to happen faster because I have an activating group. So the NAS is activated better here. The EAS is activated better here. Neither of them are wrong. Okay, on the next one, para-substituted electron withdrawing groups. So obviously one of those groups needs to be not an electron withdrawing group to begin with, and whatever happens in the last step is going to be what changes the ortho-para director. I need to add an ortho-para director and use it to ortho-para direct the nitro group. So the only thing I know at first glance of this problem is that I need to do nitration second. Well, that means that my carboxylic acid was not always an electron withdrawing group. And I know how to make a carboxylic acid by benzylic oxidation, chromic acid, hot potassium permanganate. And that requires that I have some alkyl group there. Some alkyl group that has a benzylic hydrogen. So I'm going to try and run this with methyl chloride to get a toluene. Toluene becomes nitrated. I want just the para position and then oxidize toluene into benzoic acid. What I'm trying to introduce you to is paying attention to both the directing effects and the combination of reactions that you can use. The funny thing is, this is a problem that makes sense on paper. No one in the world would go through and run it. because you can buy para nitrobenzoic acid pretty cheap. It's just getting you to think about how these reactions all piece together. Okay, the last one had an issue. Originally, I had said have two alkyl groups, but have them meta to each other, which means one of them was not an alkyl group originally. It would have been an electron withdrawing group. But that would mean that your electron withdrawing group directed alkylation meta, and electron withdrawing groups can't facilitate alkylation or acylation. So that's where I screwed up. I couldn't make you do alkylation with an electron withdrawing group. It wouldn't work. So I changed it to a bromine. Because they're meta, I know that I'm adding the meta director first, and then I'm adding the bromine. Then I'm doing something that gets rid of the meta director, turns it into what looks like an orthopara director. And I can't take a nitro and turn it into a carbon chain. I can't take a sulfonyl and turn it into a carbon chain. But I can take a carbonyl and turn it into a carbon chain. I can do reduction of ketones, reduction of aldehydes, into a carbon chain. So I'm going to show the Wolff-Kishner reduction, hydrazine reduction, which means my carbonyl, and this is what it actually looks like, that group, CH2, CH, CH2. That means that my carbonyl had this little alkene chain off the side, and it's that alkyl group that I need to add in the, or excuse me, it's that carbonyl group I need to add in the first step. So I just make sure that my acid halide has the group that I want. We are fine with adding CH3. We're fine with adding isopropyls. We're fine with adding benzene rings. We should be fine with adding these little alkenes as well. The nice thing is, if I wanted to do more chemistry, I know how alkenes react. I could do chemistry with those alkenes after this. All right, up here, N-butyl chloride is a straight carbon chain, which means the primary carbocation is going to rearrange into a secondary carbocation. I have two different directors up here. Nitrogen is an orthopara director. Oxygen is an orthopara director. What's my stronger director? My stronger activator? Nitrogen. Stronger activator, major director. So I'm going to say maybe that this chain will go para, but it could have also gone ortho. So if you did that, if you put it ortho to the amine, you had that right as well. And then this last step does radical halogenation, and that will go onto the benzylic position. So that gives us a bromine on that carbon chain that we just added. You know that it's not EAS halogenation because it doesn't have the catalyst. It doesn't have FeBr3. Once again, I have a carbonyl and I have an alkyl group. So the alkyl group is going to be my director. This is my acylation. It's just using reagents that are different from Friedel-Crafts acylation. Alkyl group, as the strongest activator, can direct ortho or para. If you showed the para substituted product, you've got it right. Are you guys comfortable with the fact that the ring on the left-hand side acts as two different substituents to the aromatic ring? It doesn't matter that these are actually connected over here. To the aromatic ring, they have two different roles. Meta director, deactivator, orthopara director, activator. And then the Clemenson reduction which takes both of my carbonyls and reduces them down to alkane. Once again, if you had drawn the para position, that would just be a different structural isomer that's possible. Same thing down here. I have an ortho-para director, so my chlorine could either go para, it could go ortho, and then the oxidation of my toluene gives me a benzoic acid. So either para-chlorobenzoic acid, ortho-chlorobenzoic acid. Synthesis is that line between creative thinking and critical thinking. This might feel a little creative. You've got to think of a structure you maybe have never seen before, but you've also got to think critically about it. I know that the alkene needs to be present. I know that it needs to be an acid halide. Critical and creative thinking merging in our synthesis problems. Okay, good luck on your unit test this weekend. I'm going to do my best to grade your homeworks tomorrow. So as many homeworks as you get turned in tomorrow, I'll do my best to grade them. I have a busy weekend. And I don't know that I'll grade your unit tests until sometime mid next week. Okay. I'll see some of you guys in lab. If not, have a good weekend.